Okay, so section 6.5, we have 3 objectives here. We're going to learn how to use our zero product property. We're going to learn how to solve quadratic equations by factoring. And then we are going to be able to solve equations with polynomial functions. Let's start with some warm-up problems. So the first one is a question where we're just simply solving for our variable y. We're going to utilize our inverse operations by adding 3 to both sides. So now we're just looking at 5y equals 3. And then our last step is to just divide both sides by 5 so that we get our y value is equal to 3/5. And we're done. Our second question is asking us to factor this completely. And anytime we're dealing with a factoring question, we want to utilize GCF. See if you can pull out a greatest common factor here. We can pull out n. And when we do, we're left with n squared minus 9n minus 22. And then we can actually now factor what we have inside these parentheses into 2 binomials. What are factor pairs of 22, really negative 22, that add to negative 9? We have a negative 11 and a positive 2. So we're really just looking at n minus 11 and n plus 2 for our fully factored form. And then last but not least, our third warm-up question. We are given a function f of x, and we are asked to evaluate it when x is equal to 3. And then we're also asked to solve when our f of x is equal to 0. So there's really 2 parts to this problem. Our part A is when x equals 3. So wherever you see an x, we're going to first draw in some parentheses. And then we're going to fill in those parentheses with 3. We'll use our PEMDAS to solve. 8 times 3 is 24. And 24 minus 16 gives us 8. So f of 3 is just simply 8. And then part B is asking us to solve when our function is equal to 0. So we get 8x minus 16 is equal to 0, and we're back to utilizing our whole inverse operations, adding 16 to both sides, and then last but not least, dividing both sides by 8. And so we simply get x is equal to 2 when our y, aka our f of x, is 0. Right. Questions at all? So the next slide is just a note slide, also a definition slide. And the first sort of section is defining what a polynomial equation is. And it's just simply an equation that contains a polynomial expression, but then it's equal to some value. And then another definition, the degree of a polynomial equation is just the highest degree of any term within the equation itself. So we've become very, very comfortable with solving polynomial equations of degree 1, aka linear equations. And so we're used to the whole mx plus b, but in an equation format, we have it as like ax plus b is equal to some numerical value. Think of all of our systems of equations. Those are polynomial equations of degree 1. But in this section, we are going to step it up a bit, and we're actually going to now be in the realm of degree 2, which is also known as quadratic equations. So polynomial equations of degree 2 is just another way of saying quadratic equation. And so what is a quadratic equation? Well, our general definition of it, which I've spoken about throughout these past, I guess, few months now, especially since we're heading into April. The whole ax squared plus bx plus c. Anytime we have an equation that has that highest degree of 2, we're looking at a quadratic equation. And this ax squared plus bx plus c is known as our general form of a quadratic equation, also known as our standard form of a quadratic equation. We'll learn about vertex form later on throughout this course. So now we're at our first objective for today, which is our whole zero product property. And this essentially says, what do we multiply our equation by in order to end up with 0 as our final result, aka zero product, right? Multiplication in order to get 0. And so our formal definition when we're dealing with just arbitrary values is what we have boxed here down below. We have 2 arbitrary values, a and b. When we multiply these together, we get 0. So essentially, if we're starting with a, what do we multiply by a in order to get 0 in the end? And in this case, obviously, a could be 0 or b could be 0, and that would give us the result that we need. These are just the step-by-step procedures in utilizing our zero product property. I think they like to overcomplicate this because the whole purpose of us understanding zero product property is in quadratic functions, when we factor out quadratics and we have 2 binomials, we set them separately equal to 0, aka utilizing our zero product property in order to find our zeros or our x-intercepts or our roots. These are all synonyms of one another. And you'll, I think, get a lot more comfortable with it when we practice concrete examples together. But that's why we're really honing in on explaining what this property means. So let's jump into our first example together, and lo and behold, we have the product of 2 binomials. No surprise here. And we're asked to use the zero product property. So what do? We look at these binomials separately, and we set them equal to 0. We ask ourselves, okay, what values of n make them equal to 0, aka our zero product property. So inverse operations, that left-hand side, we're going to add both sides by 2. And then we're going to divide both sides by 5. So our first value is when n is equal to 2/5, we get 0. And then in our second case on that right-hand side, we're going to add 1 to both sides. And then we're going to divide both sides by 6. So our second value is when n is equal to 1/6. And so if we want to plug this back in to check to make sure that this indeed works, if we plug 2/5 back in here, we end up getting 2 minus 2, which gives us 0. And 0 times anything will give us our 0, aka our zero product property. So that left-hand side works. And same goes for that right-hand side. 1/6 times 6 is 1, and 1 minus 1 is 0. Once again, 0 times anything will give us 0. And we're done. We have a little notes page / comment section. Let's see. Maybe Chris, do you think you can read this for us?
The zero product property works very nicely to solve quadratic equations. The quadratic equation must be factored with zero isolated on one side. So we must be sure to start with the quadratic equation in the standard form ax to the power of 2 plus bx plus c equals 0. Then we must factor the expression on the left.
Awesome, thanks. Yeah, so this is just making sure that we bring everything over to one side first before we jump into factoring. And then this slide is just, again, the formalized step-by-step procedure in solving quadratic equations by factoring. But we'll practice this together using a concrete example on this next slide. So what do we have to do first? If we want to solve this quadratic equation, we want to bring everything over to that left-hand side. So I'm going to go ahead and subtract 13y and subtract 45 from both sides. So we're really looking at 2y squared minus 13y minus 45 is equal to 0. And then let's factor this. Well, 2, that's our a value, which is not 1, so we need to utilize our whole AC method here. Our a is 2. Our c value is negative 45, so the product of that is negative 90. And then our b value is negative 13. So essentially, we're looking at factor pairs of negative 90 that add up to negative 13. Again, let's first start with just positive 90, and then we'll manipulate using negatives in a moment. So what are our factor pairs of 90? We have 1 and 90. We have 2 and 45. We have 3 and 30. Does 4 go in? No, but 5 goes in. 5 goes in how many times? 18, right? Does 6 go in? How many times does 6 go into 90? I think 15 times, right? Yeah. 7 doesn't go in. 8 doesn't go in. Does 9 go in? 9 goes in 10 times. And then we're done. So we're not looking at positive 90, we're looking at negative 90. So now we got to manipulate using some negatives. And so do any of these factor pairs add up to negative 13 and multiply to negative 90? Which one? The whole 5 and negative 18, right? That's the hardest part, because once you get here, now we're just utilizing our whole pulling out greatest common factors and factor by grouping. So we have minus 18y plus 5y. Right, that's the whole manipulation of that middle term, breaking it up into these two values so that we can pull out a GCF from each of these terms. We'll pull out a 2y for the first. And then for the second, we can pull out a 5. And if we did this correctly, what we have inside the parentheses should be exactly the same so that we can pull out that y minus 9. And when we do, what are we left with? We're left with 2y plus 5. And again, can't forget this is all equal to 0. We're not asked to factor this, we're asked to solve. So we're not done quite yet because we now need to utilize our zero product property. This really is a great example of showing how math really builds on top of one another, because the steps in math are becoming, I wouldn't say more complicated, they're just more tedious. We're adding on to it. Let's go ahead and use our order of operations, or inverse operations here. So one potential value is y equals 9. And then another potential value is when y is equal to negative 5 over 2. And so our last step is to test that these values work. Again, you can test them in your head. So 9, if we plug that in here, we get 81 times 2 is 162 on that left-hand side. And then 9 times 13 is 117 plus 45, which also gives you 162. So that y equals 9 works. What about negative 5 over 2? Negative 5 over 2 squared is a positive 25 over 4 times that 2, which is 25 over 2. 25 over 2 is just 12 and a half. That's what we have on that left-hand side. And then the right-hand side, we have 13 times negative 5 over 2, which gives us negative 65 over 2 plus 45. And so 45 is the same as 90 over 2. Negative 65 plus 90 is positive 25 over 2, which is once again 12.5, which is what we needed. So both of these solutions work. And we are done. All right. Do another example together. Example 3. Again, bring everything over to one side. We're going to go ahead and subtract 49 from both sides. So we're looking at 169q squared minus 49. Ooh, what stands out here? The difference of squares problem. A plus b, a minus b. What's the square root of 169q squared? 13q. And what's the square root of 49? 7. So we can factor this into two binomials. We have a 13q plus 7 in parentheses, and then a 13q minus 7, and this is all equal to 0. Now we jump into our zero product property. So we set both of these binomials equal to 0 so that we can solve for our potential values of q. On that left-hand side, we have 13q is equal to negative 7. And then we're going to go ahead and divide both sides by 13. So one potential solution is negative 7 over 13. And then on that right-hand side, after we add 7 to both sides, we're going to go ahead and divide both sides by 13 once again. So another potential solution is positive 7 over 13. So let's check to see if they work. Negative 7 over 13 squared is a positive 49 over 169 times 169 gives you 49. And so 49 minus 49 gives you 0. So that first solution works. Second one, we would get the same results because 7 over 13 squared is once again 49 over 169 times 169. Those cancel out. So we once again are left with 49 minus 49, which is 0. So these are our two values. And we're done. Let's keep on trucking along. And so I'll read this. In our next example, the left side of the equation is factored, but the right side is not 0. So in order to once again utilize our whole zero product property, we need to move everything over to one side so that we have a side that equals 0. And in this next example, what we'll do is we'll multiply the factors and then write the equation in standard form. So I'll rewrite the problem down here. Going to utilize our FOIL method. We have 3x squared minus 3x minus 8x plus 8 is equal to 3x. Then we're going to go ahead and combine some like terms. Going to bring that 3x over to that left-hand side. So now that right-hand side is 0. And a negative 3x plus a negative 3x is negative 6x minus 8x is a negative 14x. So we're looking at 3x squared minus 14x plus 8. Now we can factor. We'll factor using our whole AC method. Our A is 3, our C is 8, the product is 24. Our B is negative 14. What are factor pairs of 24 that add up to negative 14? We have a negative 12 and a negative 2. I'm going to go ahead and keep that first term, keep that last term, manipulate that middle term. So instead of looking at negative 14x, we're looking at negative 12x minus 2x, which if you add those together, you get that negative 14. And now let's pull out our greatest common factor. Between the first two terms, we have 3x, so we're left with x minus 4. Those last two terms, we can pull out a minus 2, so we're left with x minus 4. And if we did it correctly, what we have in parentheses should be exactly the same, so that we can pull that out. And so we're left with x minus 4 in parentheses, and then parentheses 3x minus 2. We're not done yet because we're asked to solve, so we need to utilize our whole zero product property, set each of the binomials equal to 0 and solve for your variable. And when we do, one potential solution is x is equal to 4. And then the other potential solution is x is equal to 2/3. And then our last and final step is to check our work. So when we plug in 4, we get 3 times 4 is 12. 12 minus 8 is negative 4. 4 minus 1 is 3. Negative 4 times 3 is negative 12. And then we have 3 times 4 is positive 12. Ooh, that does not work. Let me just make sure I did this correctly. 12. I made a mistake, right? When we plug in 4, 4 times 3 is positive 12. Minus 8 is positive 4 times positive 3. Yeah, so that does work. And then let's try 2/3. 3 times 2/3 is 2. 2 minus 8 is negative 6. And then 2/3 minus 1 is the same as 2/3 minus 3 over 3. So that's negative 1 over 3, which ends up being a positive 6 over 3, which is 2. And then that right-hand side, 3 times 2/3 is a positive 6 over 3, which is also 2. So both of these solutions work. Just want to see how much we have left. Let's try and do one more example together. And then I think what we'll do is we'll finish up this session next time. So example 5, once again, let's bring everything over to that left-hand side. So we're looking at 3x squared minus 12x minus 63 is equal to 0. And we can pull out a greatest common factor. If we pull out 3, then we're left with x squared minus 4x minus 21, which is a bit easier to factor. What are factor pairs of 21 or negative 21 that add up to negative 4? We have negative 7 and positive 3. And so then when we utilize our whole zero product property, set the whole x minus 7 and x plus 3 equal to 0, and our two potential solutions are negative 3 and positive 7. And so when we check this, what do we end up getting? Negative 3 in parentheses squared is 9 times 3 is 27. And on that right-hand side, we get negative 36 plus 63 is positive 27. So that first one works. And with 7, we have 7 squared is 49. 49 times 3 is 147. And then we have 12 times 7 is 84, and 84 plus 63 is once again 147. So both of these solutions once again work. Okay. All right, so this slide is just a note section. We have the zero product property also applies to the product of 3 or more factors. If the product is 0, at least one of the factors must be 0. And we can solve some equations of degrees greater than 2 by using our zero product property, just like we solved quadratic equations. So we'll practice that in this example 6 together. So once again, we want to move everything to that left-hand side, and we've become quite good at this point. So essentially, we're looking at 9m to the third minus 60m squared plus 100m is equal to 0. Can we pull out a greatest common factor? We can indeed. Let's pull out m. And when we do, we're left with 9m squared minus 60m plus 100 is equal to 0. And now we're going to go ahead and use our whole AC method. So our A value here is 9. Our C value is 100. The product of 9 and 100 gives you 900. and then our B value is -60. So we're looking for factor pairs of 900 that add up to -60. So there are a decent number of factor pairs of 900, but the one that sort of first pops into your head because you think of factor pairs of 9 uh, is 30 and 30, right? 30 times 30 gives you 900. And that actually happens to be the factor pair that we're looking at, especially when we're manipulating it with negatives. We add -30 and -30 to one another, we get our B value, which is -60. All right, so we keep that first term and that last term the same in our trinomial. And then those two middle terms are being manipulated into -30m and another -30m. And now we can utilize our whole factor by grouping. Pull out that greatest common factor. We can pull out a 3m, and when we do, we're left with m minus 10. Our greatest common factor with our last two terms, we can pull out a -10. And when we do that, we are left with 3m minus 10. Mistake in the first one, right? When we pull out 3m, we're left with 3m minus 10. Yeah, good. Everything looks great. This is all surrounded by that m value and set equal to 0. So if we did everything correctly with the factor by grouping, what we have in parentheses is exactly the same. And so altogether, what do we have? We have m in parentheses, 3m minus 10, close parentheses, 3m minus 10. It's equal to 0. The perfect squares trinomial, right? Dealing with subtraction. But are we done? We're not, because we're asked to solve this, so we need to utilize our whole zero product property. And so we have to set all of these equal to 0. Because it's a cubic function, we're going to end up with 3 potential solutions, right? This m we set equal to 0. So we have m equals 0. We have 3m minus 10 is equal to 0. And then we have another 3m minus 10. So those last two solutions are going to be of the same value, which means we'll just represent it as a multiplicity of 2. Let's go ahead and add 10 to both sides. And then we'll subtract or divide both sides by 3. I'm running out of space here, so let me see if I could shrink my work. So we have our 3 solutions, 0, 10 over 3, and 10 over 3, or we can write it as 0, 10 over 3 with a multiplicity of 2. And then last but not least, we want to make sure that all of these solutions indeed work. And so we plug it in. The first one is quite straightforward because if you plug in 0 for m, you're obviously going to get 0 everywhere. So that straight off the bat is a solution. 10 over 3 will involve slightly more computation, but still not too bad. We have, let's deal with the quadratic first, and then we'll just multiply it all by 10 over 3. So 10 over 3 squared is 100 over 9. And 100 over 9 times 9 is 100. And then we have 60 times 10 over 3 is the same as 20 times 10, which is 200. So we have 100 minus 200. And then we have 100 times 10 over 3 is the same as 1,000 over 3. So we have plus 1,000 over 3. 100 minus 200 is negative 100. And then let's combine the fractions by getting a least common denominator. So we'll make this negative 300 plus 1,000 over 3, which is just positive 700 over 3. And then last but not least, we're going to go ahead and multiply this by 10 over 3. I want to make sure I did this correctly because it doesn't look like it is working out. We're working with this one, right? So we got 100 minus 200. Yeah, we didn't even have to multiply that last term. So 100 minus 200 plus 100 gives you the 200 minus 200, which is 0. And 0 times any number will spit back 0. So all of these solutions end up working. And I'll even write maybe up here, therefore, m is equal to 0 and 10 over 3 in parentheses with a multiplicity of 2. Right. So we're finally on to our third objective, which is being able to solve equations with polynomial functions. And so as this whole study of our polynomial functions continues throughout this course, it's just important to know that when you're evaluating it at a certain value, so most commonly when we're given a numerical value for x, you're just plugging that into your function to spit out what that numerical output value, aka what that y value is. And from a graphical standpoint, your x and y values are just points on a coordinate plane. So how does this help us? Well, the whole zero product property when we're dealing with quadratic functions is just a really nice and straightforward way to identify x-intercepts, which is another way of looking for our roots of a quadratic equation, or our zeros of our quadratic function. These are all synonyms of one another: x-intercepts, roots, zeros. And so, yeah, we'll sort of look at a bunch of polynomial functions, now bringing everything all together. So with example 7, we're asked to find our x when we're given f of x is equal to 6. So a lot of substitution, and then simplification, and then zero product property. So again, bring everything to that left-hand side. Now we're looking at our x squared plus 2x minus 8 is equal to 0. You're now ready to factor that left-hand side into two binomials. What are factor pairs of -8 that add to +2? We have -4 and +2, so we have x minus 4 and x plus 2. And now when we utilize our zero product property, our two potential solutions are -2 and +4. Always want to check to make sure both of these values are sufficient. So go back to our original function. We're going to go ahead and plug in -2. -2 in parentheses squared is +4. 2 times -2 is a -4 minus 2, and this should all be equal to 6. So we have 4 minus 4 is 0, and then 0 minus 2 is -2. -2 is not equal to 6. So let me just make sure I did this properly. We have -2 times +2 is -4. This gives you 0 minus 2. Let's try 4. 4 squared is 16. 2 times 4 is 8 minus 2. So we have 24, and 24 minus 2 gives you 22. Why isn't this working? Did I do something wrong? Yes, I did. I factored it incorrectly, right? -4 and +2 gives you a -2x. The signs should be opposite. This should be a +4, and this should be a -2. I make mistakes sometimes too. It happens, which is why it's good to become comfortable with going back and seeing if you can identify your mistakes. And so how does that extremely vary from our final solution? It's just we're now looking at +2 as our solution and -4. So when we plug these in, that should work. 2 squared is 4. 2 times 2 is 4. Minus 2, 8 minus 2 is 6. Yep, beautiful. And then -4, that gives us +16. Minus 8 minus 2, 16 minus 10 gives you +6. So both indeed work. And we're done. So we have a notes section, and this is just stating how our zero product property helps us to determine where our function is 0. It helps us to identify our roots, our x-intercepts, our zeros, and then it leads us into 0 of a function, which again, it's the same exact thing. It's just we're dealing with function notation instead of just expressions or equations now. And it's a step up from that. We are able to plot this on a coordinate plane and determine that the function itself passes our vertical line test. We have down here our first sort of written note stating that finding a 0 of a function is where our function crosses that axis, more specifically where the function crosses the x-axis. Right, let's jump into example 8. So we're given this function, 3x squared plus 10x minus 8. And we're asked to find the zeros. So we want to set this equal to 0. We want to utilize our whole AC method in order to factor this efficiently. Our A value is 3. Our C value is -8. So we're looking at -24. factor pairs of negative 24 that add up to 10. And so off to the side, we have a few factor pairs of positive 24. And then we'll manipulate it with the negative. So we have 1, 24. We have 2, 12. Ooh. We have 3, 8, 4, and 6. And now let's manipulate with our negative. Which one can add up to a positive 10, but multiply to a negative 24, and that's our whole negative 2 and positive 12. Let's now jump into our setup to pulling out our greatest common factors and then jumping into our whole factor by grouping. We keep the first and last term the same. We manipulate that middle term 10x to be a plus 12x minus 2x. Pull out greatest common factors. We're going to pull out a 3x from that first two, or from those first two terms. And when we do, we get x plus 4 in the parentheses. And then those last two terms, let's pull out a negative 2. And then we'll be left with x plus 4, once again in parentheses. If we did this correctly, what we have in parentheses should be exactly the same, which it is. And so we're going to pull out that x plus 4. And then we're left with 3x minus 2. And once again, this is all set equal to 0. We're not done yet because we want to use our zero product property in order to determine our x-intercepts. And so we set our binomials equal to 0. So our two potential solutions are negative 4 and positive 2/3. Let's plug this in to make sure that they work. Negative 4 squared is 16 times 3 gives you 48. Minus 4 times 10 gives you 40. So now we're looking at positive 8 minus 8 is 0. That works. Now let's look at 2/3. 2/3 squared is 4/9 times 3 is the same as 4/3 plus 20/3, which is just 24/3, which is 8, and 8 minus 8 is 0. So both of these solutions work, which tells us that we have solved for our x-intercepts. Let's put that in coordinate form. We have our x-intercepts to be, definition of x-intercept is when y equals 0. So we have negative 4, 0, and positive 2/3, 0. But then we're also asked to find our y-intercept, but y-intercept is quite straightforward because what's the definition of a y-intercept? It's just when x equals 0. So wherever you see an x, you're going to plug in 0, and you'll just be left with your constant, which is negative 8. And so we get in coordinate form, our y-intercept is just 0, negative 8. And we're done. This is really like the preliminary to understanding how to properly graph quadratic functions. All right, so that was our last example for this section 6.5. I have a bunch of exercises for you guys to try on your own in our workbook so that you can get further enforcement of this material. Again, it's a lot of buildup of what we've been working on for these past few months, and it's now just putting everything together. So even though the problems are a bit more lengthy, you've seen all of these strategies before. It's just now putting everything together for that bigger picture. Hope this was helpful. Let me know if you have any questions, and I will see you guys soon. Take care.